Okay, well, welcome everyone to a new semester for TCS Plus. TCS Plus, for those who don't know or just joining, is an online TCS seminar. Um, yeah, we organize a few talks for each semester, speaking about the latest and greatest in theoretical computer science. So today is our great pleasure to have Ramakrishnan he's a student at Stanford University. He'll be talking about how to appease a voter majority. But before we begin, I do want to make just a few announcements. It's very nice for the speaker, given that this is an online seminar, if you could or unmute yourself whenever you want to ask questions, as well as leave your cameras on. This will give Pras a little bit more feedback and it makes the talk a little bit more pleasant. And I will say that after the talk, we're gonna have maybe a 15-minute session where it won't be recorded and you get to ask Pras any questions about the work or about relevant topics then. Finally, let me say that we're always looking forward to getting suggestions. So on our website, we have a form. So if you know about a result that you think would make a great TCS Plus talk, we're always happy to receive those, and um, that'll help us organize for this semester as well as for the following semester. But okay, so all that being said, I'll hand the floor over to Pras and please take it away.
Great. Yeah. Thanks so much, Eric. And thanks to all the other organizers of TCS Plus. I'm very happy to tell you about this work, which is joint work with Moses Charkar, Alex Lasota, Adrian Vetta, and Kangning Wang. Yes. Okay. So this work has to do with elections. And so the way that we typically think about elections is that we have a set of voters and we have a set of candidates. And the voters have ranked preferences over the candidates. And so, for example, here are the results of an election with 10 voters and 5 candidates represented in this table here. And so the top row of this table represents the voters' first choices, and the last row represents the voters' last choices. So, for example, here, voter 1 is telling us their favorite candidate is candidate 4, and then candidate 5, and so on until their last favorite candidate is candidate 2. And so the question with elections like these is, how do we go about choosing the most broadly appealing candidate? The candidate that best represents the preferences that were expressed by the voters. And so the reason why we're interested in this question is that this idea of voters choosing from candidates can model a wide variety of decision-making problems that we make as a society. So probably the most prominent one is a group of constituents choosing representatives in a political democracy. But you can also imagine an organization like a university or a company choosing who to hire, or a group of judges choosing the winner of a prize, like in the Oscars this past weekend, or even everyday situations like a group of friends deciding what to eat, or what board game to play, or for your movie nights or book clubs or anything like this. I think once you start to work on elections, you start to see them kind of everywhere you look. Um, and there's also been an explosion of interesting work building connections between social choice theory and AI because of the way that human preferences are used in the training and fine tuning and alignment of language models. And so this has been a lot of interesting work and all these papers here have just come out in the last year. And so with all these questions, or with all these applications, we return to this question of how do we go about choosing the most broadly appealing candidate? And so one reasonable principle that you might strive for is something called majority rule. So for example, if a majority of voters prefers candidate A over candidate B, then it feels like we shouldn't choose B rather than A. Like that seems like an awfully undemocratic thing to do. But it turns out there's a bit of a problem with this approach, which is something called Condorcet's paradox, which Condorcet came up with around the time of the French Revolution. And so he showed that there are actually elections where no matter which winner you pick, a majority of the voters will actually prefer a different candidate from the one that you picked, an alternative candidate. And the simplest such case is this election with 3 voters and 3 candidates, where their preferences are in a kind of cyclical order. So following this cycle, their preferences are like 1, 2, 3, 2, 3, 1, and 3, 1, 2. So here, if you choose candidate 1, then it turns out that 2 out of the 3 voters will prefer candidate 3. And if you choose candidate 3, then 2/3 of the voters are going to prefer candidate 2. And if you choose candidate 2, then 2 out of the 3 voters are going to prefer candidate 1. And so it's possible that no matter which winner we pick, a majority of the voters would have told us we should have chose someone else. And this result is kind of the precursor to a lot of impossibility theorems in voting theory. Probably the most famous one is Arrow's theorem. But even Condorcet's paradox can actually get a lot worse. So it turns out that it's possible that no matter which winner we pick, that 99% of the voters will actually prefer an alternative candidate. And so just to see an example, imagine we just blow up this cycle to be something larger. So here I've got an election with 10 voters and 10 candidates where they're in this cyclical kind of instance. So voter 1 has preferences 1 through 10, and then voter 2 goes 2 through 10 and then loops back to 1, and so on. And so if we choose any candidate, say candidate 5, then 9 out of the 10 voters would have actually preferred candidate 4. And you might say that this is like a little bit of a contrived instance, but it points to a kind of unsettling possibility that no matter what choice we make, like basically everyone will be unhappy. So like you imagine, you're talking with your colleagues in the hallway and you're like, I'm kind of surprised that they chose candidate 5. I thought that candidate 4 was a better candidate, and they say, I thought the same thing. And you have many conversations like this and suddenly your department chair is getting some angry emails. And so what can we do about the situation? Well, we need to relax the problem. So can we modify the goal slightly and get around this paradox? And so one idea is that if any one winner is going to cause a problem, what if we are allowed to choose multiple winners, often called a committee in the literature? So for example, if we look at this half of the voters on the right who are particularly unhappy with candidate 5, we can make them a lot happier by also including candidate 10. And now you can see if you look above this threshold that there's no longer a candidate that's preferred over both 5 and 10 by a majority of the voters. The most we could get is 4 out of 10 for candidate 4 or for candidate 9. And so it seems to kind of help with this problem a little bit. But are we cheating by kind of choosing multiple winners? Well, it turns out that this idea of committee selection actually underlies a lot of these different situations that we talked about before. So for example, it's natural to choose multiple winners for things like grants or fellowships, or when you're hiring, you can make multiple hires at once, or when you order food at a restaurant with your friends, you probably order more than one dish to share. And in the political space, there's been a lot of work on using multi-winners to get at something called proportional representation. There was a kind of interesting article in the New York Times in January about this. So if you're interested in reading more, this is something that's definitely like in the zeitgeist. Another way you could think about committee selection is as a kind of pruning step where you first want to choose a short list of candidates, and then from that short list, you might eventually choose some winners. And so, for example, choosing like nominees for a prize or a set of candidates to interview for a position, or again, in the political setting for like primaries or runoffs. And so this idea of committee selection actually shows up in a lot of different places where these decisions are made. And so with all this in mind, here is the problem that we're going to tackle. So we saw that with Condorcet's paradox, it's possible that no matter which winner we pick, a majority of voters might prefer an alternative candidate. But the question is, what happens if we can choose multiple winners? So Elkin, Lang, and Safadine in 2011 posed the following problem. Is it possible to choose K winners such that less than 50% of the voters prefer any particular alternative candidate? And so they call such a set a Condorcet winning set. And naturally, the question is like, what's the smallest K that we can get away with? How small can we make our committee while satisfying a majority of the voters? So any questions about the problem?
So
Okay, cool.
this would be a rule for choosing K under any possible like set of permutations of preferences. Is that
Exactly. So the idea is that like no matter what the preferences are, we want to figure out some way that we can choose K winners such that there's not a different candidate that's preferred by a majority of voters. And so let me point out that like this threshold of 50% can be kind of arbitrary. So it would be natural to one sec to generalize this to say that like we can have some sort of arbitrary alpha fraction of voters that might be unsatisfied. And the question that we can ask is like for each value of k, what's the best or smallest value of alpha we can get? So if we fix k, like how small can we make the fraction of voters that might have wished that we picked someone else instead? And so one thing that I really like about this problem is it feels like a very clean and natural problem, something that you could imagine Condorcet asking in the 18th century. And yet the kind of tools that we use to tackle and understand this problem are actually would not have been available to Condorcet. So the workhorses of our paper are game theory and the probabilistic method, which didn't come about until the 20th century. And we build on a lot of recent work on something called approximately stable committee selection. These papers by my co-author Kangning and some of his collaborators. I'm not going to get into these works too much in this paper, but there's a lot of discussion about it in our paper if you're interested, because we very much stand on their shoulders. Okay, but I'm getting a little bit ahead of myself, so let me tell you a little bit about what was previously known about this problem. So we saw with Condorcet's paradox that we can't always get away with one winner. And so the natural question is, what about two winners, right? And so it turns out that Elkin, Lang, and Safadine were able to show that actually two winners does not suffice for this problem. So let me show you what their counterexample looks like. So the idea is that instead of having just one cycle, we're going to multiply two cycles together. So we're going to multiply a 3 cycle by some large cycle. So here's kind of what a 3 cycle looks like. So we have 1, 2, 3, and then 2, 3, 1, and then 3, 1, 2. And so the idea is that we're going to now replace each of these candidates with a large cycle. So here we're replacing 1 with a 5 cycle, and the same with 2, and the same with 3. And so now what happens if we're going to pick a pair of candidates to be our winners? So if we pick a pair that's within the same inner cycle, like say 3 and 5 from the green cycle here, then we can kind of squint our eyes and look at the larger cycles and show that someone in the adjacent larger cycle, like this candidate 15, will beat out both of these for 2/3 of the voters, 10 out of 15 here. On the other hand, if we choose two candidates from different inner cycles, then one of these two will be the better one for 2/3 of the voters. So here, candidate 5 is the better one for 10 out of 15 voters. And so now if we look at the inner cycle, then we can choose the candidate just preceding. So here, candidate 4 will be ahead of 5 and 10 now for 8 out of 15 voters, which is a majority. And so this shows kind of the sort of problems that can arise when you have to choose multiple winners. And so the more general form of this is that you can show that if you instead have a k plus 1 cycle multiplied by a large cycle, then any k winners you pick, some alternative will be preferred by just shy of 2 over k plus 1 fraction of voters. And so this is like 2/3 for k equals 2, but it doesn't rule out winning a majority with 3 candidates, actually. Any questions about this? Okay, cool. On the other hand, so there actually been a lot of different kind of counterexamples, including some interesting work that like use computer search to find counterexamples. But interestingly, nothing has shown up that requires more than 3 candidates to win a majority. But what about on the upper bound side? So Elkin, Lang, and Safadine also showed that it's not too hard to get logarithmically many candidates. So if m is the number of candidates in total, then you can find k winners where k is logarithmic in m. And so the idea is just a very simple greedy algorithm. So if you consider the candidate that wins the most pairwise majority votes, then you can argue that that candidate has to win at least half of those votes, because that's sort of the average that a candidate would win. And so you just take this candidate, add that to your set, and then remove the candidates that it beats, and then recurse on the remaining candidates. And so each time you do this, you're going to cut the number of candidates in half. And so the total number of candidates you end up with in your set is logarithmic in the total number of candidates. And so you can get logarithmic as an upper bound. And so the question is, what's the right answer between this logarithmic upper bound and 3 as the lower bound? And so I have to confess that my first impression was that I thought that the logarithmic upper bound is probably the right answer. That this simple greedy algorithm feels like the natural thing, and so you just kind of have to figure out what's the right way to multiply multiple cycles together and get a lower bound. But it turns out that's not quite right, and so we showed that actually in any election, regardless of the number of voters or candidates or their preferences, you can always choose at most 6 winners, such that less than 50% of the voters will prefer any particular alternative candidate. And so the title of our paper is actually 6 candidates suffice to win a voter majority. And the more general version of this is that we show that if you want to choose K winners, then you can make sure that less than alpha fraction of the voters prefer any alternative, as long as alpha over 1 minus ln alpha is at least 2 over K plus 1, which is sort of a funky formula. But I want to point out that because of this lower bound of 2 over K plus 1, that this is sort of tight up to this 1 minus ln alpha factor. And so to see this a little bit better, here's a picture of like what this upper bound and what this lower bound looks like. And so let me point out kind of a few interesting points on this graph. And so here you can observe that actually with just 2 candidates, we can satisfy all but 80% of the voters, actually. So we can avoid the situation where 99% of the voters are unhappy with just 2 candidates, actually. And you can see here as well that between 5 and 6, we cross this like 1/2 threshold. And so you get more like 48% of the voters, actually, for 6. And if you go further down, like the number of Oscar Best Picture nominees, then you can make sure that all but 1/3 of the voters, roughly, are unhappy. Actually, a kind of interesting fun fact is that before 2010, the number of Oscar Best Picture nominees was actually 5, which you can see is quite a bit worse. And so you might ask, like, what happened in 2009? And so it turns out that a lot of people were really unhappy that The Dark Knight wasn't nominated for Best Picture. And there was like a huge uproar about this. And basically, this is what caused them to change the rule. People were also very unhappy that Wall-E was snubbed. So I only learned about this kind of recently, and I thought it was sort of interesting that like the kinds of considerations that we're studying here were exactly at play in this decision that the Oscars made, even before this work was initiated. Okay, so any questions about this? Okay, great. So ordinarily, this would be the point in the talk where I would tell you a little bit more about the proof, but I thought it would be more fun to tell you about a kind of interesting related thing that I think that a TCS audience might find interesting. And so imagine that I present you with the following dice game. So I give you these 4 different dice with these numbers. The dice are kind of unfolded here. And then we're going to play a game where each of us is going to pick one of these dice and then roll the die. And then whoever gets the higher roll is the winner of the game. And so the question is, if you get to pick your die first, if you get first pick, which die should you choose? And so if you look at this, you might think that you might have to do a lot of kind of annoying arithmetic, but it turns out there's actually quite a nice way of thinking about it. And so let's say that you are kind of boring and you want to choose this blue die, which always gives you a 3. Then it turns out that's not such a good choice because it's going to lose to this red die, which it gives you a 4 2/3 of the time. So then you might think, okay, maybe I should choose the red die, but that's actually going to lose to this green die because half the time this green die gets a 5 and that automatically beats the red die. And then there's also a little bit of change for when the green die gives you a 1 and the red die gives you a 0. So it's like a half plus change, which turns out to work out to 2/3. But then if you pick the green die, that's going to lose to the purple die by kind of a reverse argument. So half the time the green die gives you a 1 and that automatically loses to the purple die. And then you have some change for when the purple gives you a 6 and the green gives you a 5. And then finally, like the purple die is actually going to lose to the blue die because 2/3 of the time, the purple die gives you a 2, and that automatically loses to the blue die. And so it turns out that there is no good choice for which die to pick. And so these dice are called non-transitive dice because they have this kind of non-transitive property. Actually, these particular dice were designed by Bradley Efron, who's a statistician at Stanford. And these non-transitive dice have been thought about and studied quite a lot. So there's been a lot of research about them, including one polymath project some time ago. And And they've also been kind of a darling of a lot of like popular math media. And so kind of the origin of all this was this 1970 article by Martin Gardner in Scientific American. And so it's a really interesting rabbit hole that you can go down. There's actually a lot of different kinds of dice with different properties that you can look into. It's quite interesting. There's often one kind of funny anecdote that goes along with these stories, which is that apparently Warren Buffett is like a big fan of these dice. And he often uses it to trick his friends into paying for lunch. And there's a story that goes that one time he was trying to do this with Bill Gates, and so he presents him this game, and he says, you know, because I'm such a nice guy, I'll let you pick your die first. And then Bill spends a couple of minutes looking at the dice and doing some math, and he says, actually, you know what? Maybe you should pick first. And so I think it's sort of an amusing story. But, you know, once you know what's going on here, it's sort of no fun, right? This game is always rigged against the person who has to pick first. And so what if we modify the game so that we can give the person who chooses first a little bit of a leg up? So what if instead we allow the person who chooses first to actually pick multiple dice and then roll them and take the best roll out of those dice? So then is it still possible to rig this game? Can you still rig the game so that even if the first person picks multiple dice, they're still going to lose more than half the time? And so maybe you might see where this is starting to go, which is that it turns out that this was all just a voting problem in disguise. And so if you think of the dice as candidates, and then you think of the different points in your sample space as voters, so each possible way for the dice to roll, you think of that as a voter. And so this voter, for instance, would prefer the green over the blue, over the purple, over the red. And then, so that ordering is the preferences. Then this phenomenon that every dice loses to another die more than 50% of the time is exactly the same phenomenon as every candidate losing to another one a majority of the time. And so it turns out that these non-transitive dice are actually a particular kind of example of Condorcet's paradox, with some special sort of independence in the way that the voters view the candidates. And so analogously, there's kind of a dice version of our result, which is that with any arbitrary dice, even if the adversary has the power to produce dice with arbitrary correlations, 6 dice is always enough to get an advantage in this game. And so if you find Warren Buffett with a set of mysterious dice, then you know how to deal with the situation. Any questions about this? Okay. Eric, do you have a question? Okay, great. Sorry, I thought I saw you nod. Okay, great. So, so now let me give you a little bit of a taste of how the proof works. So I'm going to try and stick to kind of a high level, just focusing on the different ideas and what those ideas give you in the end, without really focusing too much on the details in between. So to start, let me give you just a very bird's eye view of how the proof works with this kind of one slide vision board of the proof. And so the first stage of the proof basically has the summary that randomness simplifies everything. So essentially, if instead you can choose a distribution over dice instead of just a distribution over committees rather than a single committee, then the problem becomes a lot easier. And the reason is basically that you can hit it with a game theory hammer because it's a lot easier to understand games where you can randomize over the actions rather than choosing them deterministically. And then the second stage is, what do you do with this distribution? You want to be able to choose a single committee rather than a distribution. And so the idea is to use this distribution as a kind of measuring stick. So rather than comparing candidates and committees against each other directly, you're going to compare them against this distribution. And we have this nice visual way of representing this comparison where it turns into a comparison between different areas in this picture. And then the last stage is that we want to show that some certain committee has kind of a large area. And the way you do this is by showing that a random committee drawn from this distribution has a large area in expectation. And then in the end, because of this nice kind of visual way of thinking, it turns into just a little bit of triangle geometry in the end. Okay, so this is sort of the like map of how the proof works. And so let me dive into the first stage. And so the idea is that the ideal situation that we would want to have is that we can show that we can choose a committee S of size K such that for all alternative candidates A, the fraction of voters that prefers A over S is at most 2 over K plus 1. So this here is my notation for the fraction of voters that prefers A over all of the candidates in S. And so the question is, what if instead you can choose a distribution over committees, if you can randomize over the committees? And so these earlier works showed that you can choose a distribution over committees such that for all candidates A, in expectation over the committee sampled from the distribution, the fraction of voters that prefers A over S is at most 1 over K plus 1. And so one thing to point out here is that this 1 over K plus 1 is actually better than the best 2 over K plus 1 that we could hope for. So let me point out, this is kind of like, this would resolve the whole problem if we were able to prove this. And so the guarantee that we can get for randomized committees is actually better than the best we could hope for deterministic committees. And so they call this distribution a stable lottery. And so the proof is just a very slick application of von Neumann's minimax theorem. And so let me kind of give you a rough sketch of how it works. So you can think about this as a kind of game. So I'm going to choose a distribution over committees. And then seeing my distribution, you get to choose an adversarial candidate. And then we'll draw from my distribution. And then the voters will compare whether they like your candidate more than the committee that we drew, that I drew. And so you can think of it like I'll pay you $1 for each voter that prefers your candidate over all of my candidates. And then this is a zero-sum game where the payoff is exactly this like expectation that we saw on the previous slide. And so what the minimax theorem lets us do is flip the script and say that this is equivalent to a game where instead you choose first an adversarial distribution over candidates, and then I choose a committee in response, and then we draw from your distribution and do the same kind of comparison. And so the difference in this game is that I can use your distribution against you to come up with my committee. And so the idea is just to simply, what do? You just sample K times from this adversarial distribution. And so what happens is that from each voter's perspective, if they're comparing A and the committee S, then they just see like K plus 1 samples IID from some distribution. And so they're equally likely to think that any of them is the best. So hopefully that kind of at least explains the semantics of where this like 1 over K plus 1 comes from. Okay, so any questions about this stage? Great. So the next, we're going to use this distribution to create a measuring stick. And so we're going to have this kind of visual representation that captures the information in this distribution and the preferences. And so this is what it looks like here. So I'm going to walk through exactly how it's built. And one thing I'll say is that it'll feel like we're not really doing anything as we're doing this, but I think it's kind of like when you have like nice notation or a good definition, like everything kind of falls into place very, very nicely when you have that. And so here's how this works. So this picture is like a 1x1 box, and it's split up into a bunch of different columns, and each column corresponds to a voter. So each voter V is designated one of these columns. And this column consists of a bunch of blocks that are stacked on top of each other. And each of the blocks in this column corresponds to a committee. And so there are two things about the way that these blocks are stacked. One is that the height of a block corresponds to its probability mass in this distribution delta. So the probability that we'll sample this committee S from delta is exactly the height of this block here. And then they're ordered basically by V's preference. So V prefers committees that are higher up over committees that are lower down. But you might say that we only have preferences over candidates, not over committees. And so you basically just extend the preferences to committees by saying that you essentially identify each committee with that voter's favorite candidate in the committee. And so the last thing is that the candidates are slotted between these blocks as if they're like singleton committees. And so the key thing by the way that we have arranged these blocks is that if a voter prefers a candidate A over all the candidates in S, then that means that A has to sit above S in V's column. And so this here means that because S is above A, it means that this voter must prefer some candidate in S over A. But if we look at a different voter like this voter, then A sitting above S means that V has to prefer A over all of the candidates in S. And so if we want to show that there's some S that a majority of voters prefers over any A, the idea is to argue that in this picture, all of the candidates occupy generally very low positions in this picture, while some committee is very high up in this picture. And so if all the candidates are very low and some committee is very high, then it's not really possible for for a candidate to be above the committee for most voters. And so let me be a little bit more precise about what this means. So it turns out this property that the candidates are low kind of comes to us for free by the way that this distribution delta is constructed. So we can show that for any candidate A, the area that you get under A is at most 1 over k plus 1. And it turns out that this is just exactly the expected fraction of voters that would prefer A over a committee S drawn from delta. And so if you think of K as like a large constant, like 100, like the area under A is like 1% of this picture. So A is like all of the candidates A are like really scraping the bottom of this box. And so what does it mean then for us to show that a committee is sufficiently high? Like what is the condition that would be good enough for us? So let's look at like where a committee sits in this picture. So I'm sort of just highlighting all of the green boxes here and the heights that they sit at. And so if you imagine sorting these by their height and then looking at the area for the bottom half of the voters, it turns out that if you look at this area, and if this area is bigger than 1 over k plus 1, then we're actually going to be done. And the reason is that if you look at any other candidate A, if a majority of voters actually preferred A over our committee S, then this area would somehow have to fit underneath A. And so if this area is bigger than 1 over k plus 1, then this can't be possible. And so one thing I want to point out is that like this measurement that we're doing, kind of like looking at the bottom half of voters and measuring the area under S, like it's rather than kind of comparing S one at a time against each candidate, we're kind of doing one single comparison that allows us to reason about all of the candidates at once. And so that's kind of the power of like being able to reason in this kind of way. And so how do we go about finding a committee that has this sort of area? The idea is that we're just going to choose a random committee sampled from this distribution delta. And so the idea is that if you imagine what it looks like from the perspective of each voter to sample from delta, it's as if you were to like throw a dart at this column that lands in a uniformly random height, and then looking at what block that dart lands in. Because the heights are exactly the probability that we sample them from delta. And so if you were to imagine that we could do this independently for each voter, then the shape that we would expect our committee to make would be something like this straight 45-degree line. And so to kind of convince you, like, here's what it looks like if you sample like 1,000 uniformly random points from 0, 1, and then sort them. And so this is sort of the picture that you should expect to get. To be precise, this is like the quantile function of the uniform distribution. And so if we were actually able to get this, then the area for this bottom half of voters would be the area of this little triangle here, which is exactly 1/8. And so that would be bigger than 1 over k plus 1, as long as k is at least 7. And so this would show us that 7 candidates suffice. But you might have kind of some alarm bells going off in your head because like this independence assumption seems kind of crazy. In particular, like which half of the voters this is that are captured here actually depends on the choice of S. So you really can't just get away with like pushing through linearity of expectation. And so I'll say that, you know, to see exactly how this is done, I'll let you take a look at the paper. I won't go into detail here, but just to give you some rough intuition for like why you might be hopeful about this is that the kind of bad events are in a sense kind of negatively correlated. That if one committee is like very low, then it kind of has to push up other committees. Like not all of the committees can occupy very low spaces in the picture. And so like you have this sort of negative correlation, which allows you to get around this issue. And so there, I also pointed out that this only gets you 7, and so you need a couple more ideas to get to 6. Um, and so I think I have a little bit more time than I expected. So I'll kind of tease one of these ideas for you. Um, and so the last idea is to kind of sample in a little bit more of a creative way. And so this is sort of a summary of the picture that we have so far. So we sample a committee from this stable lottery distribution, and we know that the candidates are low in the sense that the area under them is at most 1 over k plus 1. And then if we look at the bottom half of voters, then the area under them, under the bottom half, is this triangle here, which is at least area 1/2 alpha squared. And so we get a contradiction as long as 1 over k plus 1 is less than 1/2 alpha squared. And so the idea is like, what if instead of sampling just one committee of size k, you try and sample 2 committees of size k over 2? And so what you get as a result is that your guarantee for the candidates being low is a little bit less strong. So you get like a k over 2 instead of a k in the denominator here. But analogously, you get a stronger condition for the committees being high. So rather than following this 45-degree line, you get them following this like square root curve. And the reason for this is because of a nice fact that if you take 2 uniformly random heights and look at the maximum, that's equivalent to taking 1 uniformly random height and taking the square root. And so you end up with this picture instead, and the area you get is like this integral from 0 to alpha of root alpha. And so you get a kind of different condition where you get a contradiction, which turns out to be a little bit better for large values of k. And so you could do this again, like sample 3 committees of size k over 3 or 4 committees of size k over 4. But then it becomes like an absolute mess to figure out like what's the best of these to pick. And you're making all kinds of integrality assumptions about the size of the committees, which doesn't really quite work out. But the idea that you can do to get around all of this is to instead just work directly with this function that is the quantile function of what these committees follow. And so it turns out that you can essentially kind of argue with a more or less arbitrary function, g of x. And then you get this area to be the integral from 0 to alpha of g of x. And then this area on the left here corresponds to the integral of g of x to the k. So you can check, for instance, if g of x is x, then this integral is like 1 over k plus 1. And so like if you open up the paper and you see a bunch of integrals, this should hopefully kind of more or less explain why. And so let me kind of start to wrap up with a few kind of concluding thoughts. So to conclude with just a little bit of philosophy, looking back on all of this, I think that because of the role that elections play in our society, we can have kind of a lot of baggage around them because like elections are so closely tied to politics and politics are so fraught, but sometimes that baggage can kind of limit our perspective. So sometimes like when I talk to people about voting with randomness, it can sound like very scary because like the idea of like making a very big decision and leaving it up to chance is like a terrifying thing to do. And you know, one answer to this is that like that we saw kind of at the start of the talk is that elections are a lot more than politics. So there are a lot of different decisions outside of politics that can kind of be thought of in terms of elections. But I think that there's also kind of another interesting perspective, which is to think of elections as kind of another sort of fundamental mathematical object, sort of in the mold of like a graph or a partially ordered set. Like maybe anytime that we see a collection of orders or a collection of permutations, like it's like the numbers on these dice, it's like very reasonable to try and use our understanding of elections to try and say more about them. And so with that perspective, I think it's exciting to think about elections sort of from the perspective of like a pure mathematician and kind of like try to understand everything we possibly can about them with a sort of unencumbered curiosity. And so with that, I'll conclude with some takeaways here on the slide. Thank you very much for listening. And I'm happy to take any questions.
Okay. So actually I had a question for us, and we can also, if
Yeah.
people want, then move to the offline session. Um, so I thought there was a gap between what you can do with the distribution of 1 over k plus 1 versus 2 over k plus 1.
Yes.
Where did
Let me see.
Where did
Let me
this
see if I can pull
go?
that slide up here.
Yes.
Yeah. Yes. Yeah. So yeah, there is a gap between what you can do with a distribution and what you can do with picking one committee deterministically.
But at
Were
the
you
end,
asking
you
like
are
why that
picking
is, or
at the end you are picking a committee that like you're picking a single committee and you're getting the one over. So what where is this?
yes.
At some point you have to lose this factor of two.
Uh, yes. So you are in the end picking a deterministic committee, but the way that we're picking that committee is kind of non-constructive. So we're showing that when we sample a committee from this distribution, that like when you analyze it in some kind of expectation, like you get a reasonably good committee with respect to this guarantee. Um, and so yeah, you do kind of have to lose. You lose actually more than this factor of two. Um, you lose like this like additional like one minus one alpha factor as well. Um, yeah.
I see. Okay. And so, okay, this is probably part of the analysis that you didn't go over.
Yeah. I think yeah, if I had to say like exactly where that factor gets lost, I think that it's maybe not so easy to like exactly pinpoint, but yeah, there's kind of a lot of different steps here where like we're more or less what we're trying to do in one sense is like round this distribution. Like we're trying to round this distribution to like a deterministic single committee. And so like as we're doing this kind of rounding, there's like losses that happen in these areas and whatnot. Yeah.
Okay. If there's any other questions, I mean, can feel free to unmute yourself. I'll give a couple seconds, and if not, we can go offline. Okay, so let's do that. I'll stop
Great.
the
All right.
recording.
Thanks, everyone.